Alright, ladies and gentlemen, welcome back to the wonderful world of videos. Okay, we're going for 12.1 now, Introduction to Limits. The objective pretty short and sweet. We're evaluating limits. Remember, evaluate means we're going to get a numerical answer. At least most of the time we will. Alright, well, the definition of limit, as you can see right there, is a little bit mathy, so I apologize for what this is going to sound like, but here it goes. If f of x becomes arbitrarily close to a unique number L as x, again, approaches c from both sides, the limit of f of x as x approaches c is L. Alright, doesn't that sound wonderful? And this is written as, okay, limit right there, the LIM means limit. Okay, the x arrow c means x approaches c, and then of course f of x is f of x, then equals L. Alright, so again, very mathy sounding, but, okay, so if I write this with a little bit less messiness to it, you can see right here how it translates. The limit as x approaches 5 of f of x equals 12. Alright, so that's how that's read. And basically, you can see the green and the red. Those can be interchanged depending on how you want to read it. Some people like to say the limit as x approaches 5 first, so they like the kind of bottom one first, of f of x equals 12, or quite honestly, I usually say the limit of f of x as x approaches 5, so I kind of say the top one normally. But really, it doesn't matter which way you want to read it, but that's the way it goes. Okay, I'll take another step toward turning it into English. Well, sort of. Okay, so here we go. If the maybe with an example this will work better. If the y values of a function are approaching the same value on both sides of a particular x, the limit of the function at the x value in question is that y value that you've reached. Alright, so let's try this. Graphing 1/2 x squared plus 1, and then we're going to evaluate the limit, but let's get the graph done first. Okay, of course, 1/2 x plus 1 means I just need to start up 1. And then again, remember the 1, 3, 5 kind of stuff means that I can go over 1 up a half, and then over 1 up, well, half of 3 is 1 1/2, so I go the other half and up 1, so there you go. And if I wanted to, I could go over 1 and up 2 1/2, so I'd be kind of at the very top edge of my graph here. Of course, since it's a parabola, it's nice and symmetrical, so I can give a bunch of dots going the same way, going the other way. But realistically, what I care about here is going to be the x value of 2. But I'll get my whole graph here. Alright, change color so it's dramatic. Alright, so I would not want to evaluate the limit of f of x as x approaches 2. Okay, so again, basically what I'm worried about is the x value of 2. So there's my x value of 2. And again, basically now I'm looking up here at the function. Alright, now from the left side, my function seems to be approaching the y value of 3. And from the right side, as I kind of just put my pencil somewhere on this function and kind of trace it back toward 2, okay, so I'm over here at almost an x value of 3, and as I come back toward the 2, I get really, really close to 3 here. If I start like a 1 and trace along my function until I reach 2, I also approach 3 from this side. So basically, what we can say here is the limit of our function, which again is the 1/2 x squared plus 1, as x approaches 2 is going to be equal to 3, because that's the y value we come to from both sides. Alright, so there it is. I guess the final answer is really just the 3, but there's a nice fancy way to write the whole thing using all our new function and limit notation. There it is. Hopefully that made a little bit of sense. Alright, let's take a look at a graphical one where we're actually given the graph. And admittedly, this thing looks like some kind of a piecewise function of two linear functions kind of stapled together, if you will. The equations aren't important, though, because we do have the graph already. So let's see if we can just evaluate the limit of our function here as x approaches -3. Alright, so really what we care about is finding our x value of -3, and that's going to be right here, of course. There's our -3. Alright, and then again, I want to worry about going from both sides. And so let's go over here. So maybe here's this -3, so maybe I'm over here at like -4 point something. And if I kind of track along my graph up back toward the value that I care about, in this case the -3, seems like I'm getting right over here to a value of 4. Alright, now that's from the left. If I come from the right side as well and start over here like -1 or something like that, and trace my graph back to the x value in question, from the other side I'm also going right to the value of 4. And so, pretty simply, what that allows us to do is say, hey, the limit as x approaches -3, the limit is then basically just the y value, where that happens, and in this case that y value is 4. Alright, moving along. Alright, so you might be thinking this is really, really simple. You're just basically reading coordinates of a graph. Well, to a degree that's been true so far, but there are some ways we could throw a monkey wrench into things, and here's one of them. Alright, so evaluating this piecewise function as the limit approaches 1. Alright, so again, what I'm worried about is my x value of 1, so I'm kind of looking right here. Alright, well, again, if I'm on the left side of this thing, like I started 0 or negative 0.5 or something like that, and I trace down, it looks like I'm heading towards negative 2 as far as a y value. Okay, but if I'm coming from the right side, again, I'm over here like negative 2.5 or something like that, as I trace back to the value that I care about, looks like I'm getting pretty darn close to 3. Now granted, it's an open dot, so I'm not exactly making it to 3. I'm like at 3.0001, you know, that kind of deal. Okay, but since I'm not approaching the value, or the same value from both sides, okay, this one, the limit, does not exist. Alright, and hopefully there's something going on in your head, and I wouldn't have any idea what that might be or anything like that, but, you know, there it is. So it's not just as easy as reading coordinates. It's possible that the limit plain old does not exist. Alrighty, so let's start using our calculators a little bit, see if they can help us out and see if we can interpret what they're giving us. Alright, so for instance, okay, we want to use the graphing function of our calculator to graph each function here. We're going to do a few examples like this and determine if the limit exists. Alrighty, so we're going to evaluate the limit of f of x for, well, as x approaches 5 for this function right here. So of course we type this in our calculator and graph it, and we get something that looks like a line. Hopefully that's not too mysterious if you remember our rational functions. Alright, because if you think about this thing, if I graphed this, or actually better yet, if I factored this, alright, this would factor in x plus 1 and x minus 5, and then the x minus 5 down here would actually cancel, so this is really the graph of x plus 1, but if you remember, since we have a common factor, and actually let me write these things out so I'm not totally talking to thin air here. So again, x plus 1, x minus 5 is what this guy would look like in factored form. X minus 5 on the bottom would cancel each other out, but realistically what that does is it gives us a hole at x equals 5 in our graph, although the graph looks just like the graph of y equals x plus 1, as you can see. Okay, so it's one of those things that if I try to evaluate for x equals 5 and I just simply, you know, go to the table in the graph or something like that and go to 5, you know, it looks like you go up here and get some kind of value, but there's really a hole there that, remember, our calculators won't show. So if I try to evaluate this at x equals 5, the calculator's plainly going to yell at me, say, hey, what are you talking about? Alright, so basically we have to work our way around it, and okay, a couple different ways is we could evaluate this thing at, you know, do x equals something really, really close to 5, like 4.99999, you know, just type in a few nines, okay, and it'll give you something really, really, really close to 6. Alright, so with the 4.999, it'll give you something along the lines of 5.99999. Okay, at the other side, we can plug in something a little bit above 5, so 5 point, throw down a few zeros, and throw 1 there, and you know, what this thing should give you is something around 6.0001-ish as well. Alright, so basically you can see that we got really, really close to 6 from the left, and we got really, really close to 6 from the right, so even though if I try to evaluate this in the table or using the functions of the calculator, it's going to say no. Basically what happens is the limit here is actually 6, and again, you can probably interpret that from the graph, but actually some of the functions of the graph and the calculator can get that job done for you as well. Alright, here's another one that I think is a little more cut and dry. Okay, if I do a limit of f of x as x approaches 3 of this particular function here, alright, I should get a picture of something like this. I just restricted my window from -2 to 8 here to not leave a bunch of stuff on the left that I really didn't care about. Alright, so again, pretty obviously we have a bad value of 3 down here in the denominator, so it does generate something from the graph. And again, depending on your model of calculator, you may or may not get this vertical line right here, because that is basically an asymptote. So it's just a vertical asymptote right there for our graph. Okay, but again, as I'm approaching 3, notice from the left side of this thing, as I go through 1 and through 2, I kind of dropped off to negative infinity. Again, remember this guy does keep going forever. And as I come at the value of 3 from the right side, as I count back from 7 to 6 to 5 to 4, this guy takes off and goes to positive infinity. Alright, so basically you know what that means. The limit does not exist. Alright, here's another unusual one, at least I think it is, but here we go. Okay, the limit of f of x as x approaches 0 for cosine of 2 pi over x. Okay, so what I did here is I graphed this guy from negative 2 pi to positive 2 pi. And it looks a little bit messy right there, so it's a little hard to tell because, again, I'm going for 0, so I'm looking for an x value that's right here in the center of all this mess. Okay, so what I did then is I regraphed this thing from negative pi over, just kind of picked 8, sounded like a fun number to me at the time, and positive pi over 8. And again, notice the y just goes from 1 to negative 1, which hopefully is not a surprise since we're dealing with cosine. No matter what you plug in, it goes somewhere between negative 1 and positive 1. Alright, and again, as I take even this little sliver of the graph, I'm only, again, negative pi over 8 to positive pi over 8 means I'm only a total distance here of pi over 4. Okay, and you can see this thing, as I get closer and closer in toward the origin, this thing starts wildly oscillating positive versus negative. Okay, so basically what's going on here is, since I never zero in on any particular value, and if you don't believe me, feel free to pick a smaller sliver of the graph repeatedly, go over and over and over, and again, you're just going to get this big nasty mess. Basically, here's another situation where the limit does not exist. Okay, again, if you'd like to abbreviate the limit does not exist by using DNE, I'm totally okay with that, and I'm sure there's one other person who would probably be okay with it as well. Well, we spent most of our time talking about graphing, but let's go on and not use some graphing here and see if we can kind of take an easier route. Depending on the situation, sometimes a graph is the easiest way to go, but not always. So here we go. If I'm going to evaluate the limit of f of x as x approaches negative 4 for this function right here, again, right off the bat, that's a parabola. So of course we can go ahead and graph that guy without too much effort. But realistically, since I know it's a parabola, I know it's this completely continuous curve and there's no breaks or anything crazy like that, and there are holes in the graph. So really the easiest thing to do in a situation like this, where I have a very recognizable sort of function that I know doesn't have any craziness to it, all I got to do is plug it in. So basically, we're just going to plug in the x equals whatever value we're talking about, in this case negative 4, into our function. So we're just doing f of negative 4. Because again, I know it's going to be coming the same value on both sides because I have a parabola and it's a nice, easy, simple curve sort of thing to deal with. So we simply plug in our negative 4, crunch the numbers. That's going to be a 16, that's going to be a 36, that's going to be a 5. And I'm pretty sure that 52 plus 5 is about 57. Alright, so basically there, our limit is 57 without going through the trouble of a graph, because quite honestly, in this case, we had something that was easy enough to work with. Alright, well from there, there's the assignment. Any questions, please do ask. I'll see you in class.